This video provides some help with question 11 on the Chapter 9-1 problem set. And so this is a problem about calculating the pH and fraction dissociation alpha of a couple of weak acid solutions, actually the same weak acid solution, but at very different pHs. Not at very different pHs, at very different concentrations. So our formal concentration are quite different in the two parts of this problem. So basically what we have here is a weak acid. So this weak acid is acetic acid. So acetic acid has this formula. And it's the hydrogen atom that's attached to the oxygen atom. That is the donatable proton. So that's going to be our weak acid species. And so when this breaks up, we're going to end up with dissociating an H+ ion. And then we're left creating the conjugate base species, the acetate polyatomic ion, COO-. And so there's a -1 charge on that oxygen that the H left. Okay, so this is a typical weak acid problem. So we've got our Ka equal the H+ molarity at equilibrium times the equilibrium A- concentration. A- is just our acetate concentration, divided by the equilibrium undissociated acid, HA concentration. And so that'll be the undissociated acetic acid here. Okay, so we were not given the Ka, we were given the pKa. So we're going to need to find that. Remember that Ka is equal to 10 raised to the negative, don't forget your negative sign, pKa power. And that's just what we get when we solve this equation for pKa is equal to negative log of the Ka. So when we solve this equation for Ka, we get this one. All right, so we're just going to take 10 and raise that to the negative 4.756 power, and that will give us our Ka value. Then you'll remember we can use our Rice table, and we substitute in here, we get x squared over f minus x equals whatever our Ka value is that we just calculated, right? And then we want to take this equation and solve for x. So in this case, it's going to turn out that our formal concentration right here, this thing that I call F, that's just the molarity of our acid. So in the first part of this problem, that number is going to be 0.00273. All right, so that's like, if I move my decimal place, like 2.7 times 10 to the negative third, and it's going to turn out to be pretty close to the exponent of our Ka value. So probably we cannot use the small x approximation here, and we're going to need to use the quadratic equation. All right, so we do a little bit of algebra here. And we can rearrange this equation so that it looks like this. All right, so this equation has quadratic equation form, and so our A coefficient is just going to be 1 because 1 times x squared is 1. Our B coefficient is going to be Ka, so ax squared plus bx plus c, so our C coefficient is going to be negative, and don't forget the negative sign, Ka times our formal concentration. And then we now know what all of these things are, so we can substitute into a quadratic equation or the quadratic equation solver if you want to find one of those online, and solve for x. So x will be our H+ ion concentration at equilibrium. And so from that we can find the pH using our normal formula. pH is equal to the negative log of whatever that number is, H+ ion concentration at equilibrium. And so that'll give us the pH number, and that will be the number that we can put into this first blank. To figure out the alpha fraction, alpha is going to be the fraction that's in the conjugate base form, so the fraction that's dissociated. So that'll just be the equilibrium concentration of our A-, divided by the total acid that we have started out with, and that's just our formal concentration. And so this is just going to be x that we just solved for, divided by f. And so we can just do those two things to solve for our problem. So that's the first part of this problem. The second part of this problem is a little trickier, and the reason is that this molarity is so very tiny that yes, we have a weak acid, and a little bit of it is going to dissociate, maybe even a lot bit of it is going to dissociate. So we're going to be adding a little more H+, but it's a tiny molarity. Even if this were a strong acid, we would be donating just a little over 10 to the minus 12th moles per liter of H+. Remember, however, that we have another source of H+ in our solution, because water, which is our solvent, just floating around there, can dissociate a tiny little bit. We know this doesn't happen very much, but the autoprotolysis reaction says we get H+ and hydroxide. Now, water is neutral, so we'll have equal quantities of these two, but this is governed by the equilibrium constant that we call Kw, which at 25 degrees Celsius is 1 times 10 to the negative 14th. So we do have a little bit of H+, and if this were pure water without anything dissolved in it, our equilibrium H+ concentration would be 10 to the minus 7th molar, and we worked out what that was. So we sort of need to account for this autoprotolysis reaction when considering this molarity. So what we're going to do is rework our rice table problem and think about it again. So here's our reaction. We've got our acetic acid donating a proton and forming acetate. So we want to write down our initial amounts. So the initial amount of acetic acid that we have before anything dissociates, that's just our formal concentration, what we've been calling F, and so I will continue to do that, but I will write up here above it what that number is. And so in our particular version of this problem, it's 2.49 times 10 to the negative 12th. So 2.49 times 10 to the negative 12th moles per liter, so not very much. And then over here for H+, now normally we would say that none of this is dissociated, so we would have no H+ in our solution. But if we had pure water here, we would have this much H+ in our solution. So as an approximation, we're going to substitute that in as our initial amount. So we're going to have 10 to the minus 7 moles per liter of H+, and still initially 0 moles per liter of acetate because none of it has dissociated. So for our change, some of this acid is going to dissociate, so we're going to lose, we don't know how much, X moles per liter. So by stoichiometry, if we lose X moles per liter, we're going to gain plus X moles per liter of H+, and plus X moles per liter of acetate. So then we just add down the column to figure out the equilibrium values. So that's going to be F, which is this number, right? Minus X, which we don't know. Then we're going to have 10 to the minus 7 plus X, and then X. So we substitute this into our equilibrium constant expression. So these are all equilibrium concentrations, so we want to use our E-line values here. And so we're going to get 10 to the minus 7 plus X. And then for our acetate, our concentration is X. For the acetic acid, undissociated acetic acid, it's F minus X for that concentration. And so that's going to be equal our Ka value that we figured out in the first part of this problem. So now what we need to do is figure out how we can solve this equation for X. So we're going to go ahead and treat this as a quadratic equation. So I need to rewrite this equation in quadratic equation form. So let's go through the math here. So in this numerator, we're going to multiply the X through there. So we have 10 to the minus 7 times X plus X squared over F minus X, and that's all equal to Ka. So to try and solve this for X, I need to get all of my stuff on one side of the equal sign. So I'm going to first do that by multiplying both sides of this equation by the denominator here, that F minus X. So I'm still going to have 10 to the minus 7 times X plus X squared, that's from the numerator, equals Ka times F minus X. So now I can distribute my Ka through this equation here. So I'm going to have Ka times F minus Ka times X. So now what I can do is move everything from the left-hand side of the equation over here to the right-hand side of the equation. So I have 10 to the minus 7 x plus x squared, so that stays. And then what I'm going to do is subtract Ka times f, so this bit, from both sides of the equation. And then I need to, because this is a minus sign right here, I need to add plus Ka times x to both sides of this equation. And then I'm going to be left with 0 over there on the right-hand side of the equation. So I know this looks a bit messy, but you see that I have two bits here that both have a number, 10 to the minus 7 or Ka, times x. So I've got a sort of common factor here, and so I can group those together. So I end up with x squared, that bit, and then I have plus 10 to the minus 7 plus Ka times x. Okay, so that's what I get when I sort of group these two terms together and factor out the x. And then I still have my minus Ka times f, and that equals 0. So you'll see this looks like quadratic form, ax squared plus b times x plus c equals 0, where a, again, is going to be 1. B now is going to be equal to 10 to the minus 7 plus Ka, so those are two numbers, and I can just add those together and figure out what that is. And then C is going to be the negative, don't forget your negative sign, of Ka times our formal concentration. So again, we can plug all of these into a quadratic equation solver and figure out what x is. And x will be our H plus ion concentration, and from that we can figure out what pH is. And then we can figure out what our alpha fraction is, because it's going to be x divided by f. And so after we've done all this math, we'll be able to know these two values that we can plug into our answer boxes up here. And as a hint, since this concentration is so very tiny, our pH here is not going to be very different at all, in fact, maybe not at all, from the pH that we would see in pure water, because we've really got just a tiny, tiny amount of acetic acid in there, right? 10 to the minus 12 molar is super small. And it'll be interesting to see what our fraction dissociation is there. So is this a weak acid? Does it essentially 100% dissociate, or is it just a little bit dissociation? What are we going to find? So is our alpha fraction close to 1, like it would be for a strong acid, or down around a really small number? So we'll wait and see what our alpha fraction works out to be. So grind through the quadratic equation. You're going to need that to solve. Use your quadratic equation formula, again, just as a reminder of what that formula is. Or you can use a quadratic equation solver, but x is equal to negative b plus or minus the square root of b squared plus 4ac, minus 4ac over 2a, 2 times a. So plugging in your a's, b's, and c's here, you can plug them into this equation and solve for your two roots. One of them is going to be negative, one of them will be positive, so pick the positive root because we cannot have negative molarities, right? That doesn't make any sense physically. And or you can use a quadratic equation solver online and plug in the values of a, b, and c, and you should get the correct answer. Again, let me know if you still have questions about this problem.